Hi everyone. This video is the solution to example 2 on the topic of flexibility method. As in the previous case, this is a structure that has 4 reactions. So we can count them as VA, HA, and then VC and HC. As we know, we need to remove one of the reactions to make sure we get a structure that we know how to calculate. And then we're going to use the compatibility equation to get that reaction. In this case, I'm going to choose to remove HA from the structure, and we're going to then calculate the horizontal displacements at A, so then we can use the compatibility equation. Our final structure, our original one, is nothing more than one that has the support at C like this, but then at A, instead of having a pin support, we're going to have a roller because now we don't have the horizontal reaction. The loads of 24, which is all the loads we have in the system, 24 kilonewton per meter, will stay in this structure, and then we can add another structure that will have a load of 1 kilonewton, and again the support here is the same as before, but we put a 1 kilonewton load in the position of HA. So then when we multiply this by the reaction HA, we have an equation to calculate HA. Okay, so this is the setup of the problem. What we need to do next is find the bending moment diagrams for both of these cases. So let's calculate here bending moment diagram for structure number 1 and bending moment diagram for structure number 2. So for structure number 1, it might be useful to calculate the reactions just to make sure we don't make any mistake. So if we think about the reaction on the structure on the top, the horizontal one here has to be 0. And then if we want the sum of moments at C to be 0, this reaction VA needs to be the one that multiplied by 6 gives me the same moment as the UDL. So the UDL is 24 times 6 times 3, that's 432, and then I divide this by 6 to get the reaction at A, which is 72, which means this reaction here is going to be nothing more than 24 times 6 minus 72, which also gives me 72. So okay, with these two reactions, we can start understanding that the bending moment diagram has to be 0 in the column, because again we don't have any loads and we don't have shear force in this column. So then here is going to be 0. It has to be 0 at A as well. So here we have a parabolic moment, and here in the middle the moment is nothing more than WL squared over 8, which should be equal to 24 times 6 squared divided by 8, which is 108. Another way to get this moment could be 72 times 3 minus 24 times 3 times 1.5. Should give you the same answer. Now we have this bending moment diagram. We still need to calculate the second structure. So similar as before, let's do the reactions first here on the top. So what we know is we have 1 kilonewton to the right. So this reaction here has to be to the left, also 1 kilonewton. And now the entire torque caused by these two forces, since this distance here is 3 meters, is 3 kilonewton meter. And this is a counterclockwise torques, right? So the reactions are doing this motion. So what we need to do is the opposite motion, so something that looks like that, which means this reaction here has to be up and this reaction here has to be down. So it does that motion. So if we know the torque is 3 and these reactions have to be the same, and this distance here now is 6, that means these reactions have to be 0.5. So what we're saying is that 0.5 times 6 has to be equal to 1 times 3. And now the moments are in equilibrium. So with these reactions, we can start understanding that we're going to have moments in the column on the left side. So the load of 1 kilonewton here, this one, causes our bar to bend like that. So we're going to have tension on the left side. And we know we always draw the diagram on the side of tension. So this moment here is going to be 1 times 3, so it's going to be 3. We know this transfers outside, so it's going to go there to 3. And now this should close back to 0, like this, but let's confirm. We can confirm by saying, okay, we have this load of 0.5 here. This will bend my structure like that. We'll push it down. So that means tension on the top, which is correct. And then the value will be 0.5 times 6, so that will give me 3. So this diagram looks pretty good. Now, our next step is to calculate the horizontal displacement at structure 1. So the first thing we need is this displacement here, horizontal displacement at A for structure 1, and then also calculate in this structure the horizontal displacement at A in structure 2. So let's do first the one from structure 1. What we know in this case is the diagrams in the columns, so that will be 0 times a triangle, so that's just 0. If you want, we can divide by the EI of the column, plus the parabola times a triangle divided by the EI of the beam. So we know the first one is 0, and the second one is parabola times triangle, that's 1/3 ACL. And again, we need to think about this is the values on the parabola and on the triangle. So 1/3 times A is the maximum value, so it should be 108. C should be 3, and then the length in this case is 6 meters. This gives me 648 divided by EI. But now we need to think about the signs, and in this case, since this diagram here is positive in this case, so tension on the bottom, and this diagram here is tension on the top, when we multiply these diagrams, one of them needs to be negative. So one of these values, either the 108 or the 3, should be negative. So this means this value at the end needs to be negative, which means that the load we're assuming in the beginning, the displacement is going to be in the opposite direction. So we're assuming the 1 kilonewton to go to the right, which means this displacement actually goes to the left. Now, before we continue with the solution, let's just stop and think if this makes some sense. If we look at the structure with the 24, so if we look at this structure number 1, we can see with these loads, the reaction at A, the point at A will most likely open up and move to the left. So that kind of makes sense that the displacement at the end gives me to the left. So okay, I'm happy with these numbers. The next thing we need to do is the horizontal displacement at A for structure 2. And in this case, we know that it's nothing more than multiplying the diagram from structure 2 by itself. So in this case, what we're going to do is a triangle times a triangle. This is for the column, plus a triangle times a triangle, and this is for the beam. In this case, both cases will be positive because we're multiplying the diagram by itself, which means they are on the same side. So in this case, we're going to have also 1/3 ACL, so for both triangles, but we need just to pay attention to apply this correctly. So for the columns, both A and C are 3, and the length is also 3. We can see in the problem over there. And then for the other triangle is 3 times 3 and now times 6. So carefully substituting, this is 1/3 and then 3 3s, and then plus 1/3 and then 2 3s and then a 6. And don't forget here, this should be divided by the EI of the column and this the EI of the beam. Because in this case they're the same, we can add them up. So the final solution here is 9/EI plus 18/EI. So at the end we get 27/EI. And in this case, since it's positive, this is nothing more than moving it to the right. This is always positive because if we're assuming the load to go to the right, and here we're going to look at this unit load here, the displacement also has to be to the right. So in all of these cases, the displacement will be positive. Okay, so now we figured out that our structure 1 wants to move to the left 648 EI, and then a unit load of 1 moves it to the right 27 EI. And what is our compatibility equation? Is to say that the actual horizontal displacement at A needs to be 0. And we know that this is nothing more than the 1 from structure 1 plus the 1 from structure 2 times the reaction HA that we're interested in calculating. And this has to be equal to 0. By replacing with the values, this is minus 648 divided by EI plus 27 divided by EI times HA equals 0, which then at the end says that HA is going to be positive, so it's 648 divided by 27, and also don't forget the EI simplify in this case. So 648 divided by 27 is equal to 24 kilonewtons. Now, the fact that this is positive means this pushes it to the right, because that's what we're assuming our unit load to be since the beginning, always to the right. Which now actually it makes sense, because when we removed the support, the point, so this point here, wanted to move to the left, so then it makes sense that the reaction pushes it to the right, so then the displacement goes back to 0. And this is it. So now the final step is to get the final bending moment diagram, and this is nothing more than taking the bending moment diagram from structure 1 and adding the one from structure 2 times the reaction HA, which we know it's 24, but let's just write it as HA for now. And then we're going to substitute it with 24 in the next picture. So very, very quickly, we know that this diagram looks like this, and that value over there is 108. And we know this other diagram looks like this, with 3 in the corner and then 0. And this is the diagram we're going to multiply by 24 to get our final bending moment diagram. So let's do this. Draw a really big diagram here to make sure we have space to draw everything. So if we look at the column, on diagram number 1, so on structure number 1, we don't have any moments. So the only thing we need to do is keep the 1 from structure 2, and then the value here in the corner is going to be 3 times 24, 72. And we keep the same direction because HA is positive. If HA was negative, then our triangle would need to be drawn on the other side of the column. So okay, we now know that this 72 is going to be transferred outside, which also makes sense because the moments there and there are still the same, right? So we still get the 72. And I think the last one we can calculate is the moment in the middle. So if we want to know the final moment here in the middle, we have to look at this 108 and then look at this value in the middle, which should be 1.5 times 24. So the 108 should be bigger, so it's going to be on the positive side of the diagram. So it's going to be 108. Since the 108 is positive and the 1.5 is negative, I'm going to put here a minus sign because they're in different positions. So 1.5 times 24, and this should give me the final moment in the middle, which is also 72. Now, to close the diagram, we can already do our parabola because we know it's a UDL. But if you want to think about mathematics, this is a quadratic function, this is a linear function, so that at the end, when you add them up, you're going to get a quadratic. And this is it. This is the final answer for your structure. Thank you for watching and have a nice day.